Today I will talk about some basic discriminative model, and discriminative model is a method to evaluate the posterior distribution directly and without evaluating the joint distribution, because it's using a nonlinear function to model the posterior distribution. Here I use a hat to represent the vector, and A is equal to the linear combination of x n, and omega is a parameter. And to evaluate a parameter omega, we can use maximum likelihood estimator, and we also know that there's some disadvantages in using the maximum likelihood estimator, such as it can produce overfitting and cannot do online learning, and is sensitive to the outlier. So today we'll talk about the discriminative model from the basic perspective. And so we're using the maximum posterior estimator to evaluate the parameter omega. So according to the basic rule, we can write the P omega given T
What is n?
N is suppose we have the side of the data. N, N is the index of the side of the data. And we know that to calculate the posterior distribution, we need to calculate the joint positive distribution and the model evidence. And model evidence is equal to the integral of the joint positive distribution respect to the Tn. So sometimes it's not easy or intractable to evaluate the model evidence. So we cannot calculate the posterior distribution directly. We need to resort to some approximation method. And today we'll talk about Laplace Approximation method, which is simply and most widely used approximation method. And now we talk about the Laplace approximation. And first, we will consider the simple scalar case. We consider a single continuous variable z and the distribution, the scalar case. Single continuous variable z. So the true distribution Pz, we can write it equal to the capital Z Fz. So the capital Z is a non-negative factor is equal to the integral of Fz with capital Z. So we want to find a distribution Q of Z is equal to the Z tilde F tilde Fz. Because I forgot to mention that here the non-negative factor Z is unknown, or is not easy to evaluate. So we want to find a distribution Q of Z equal to this equation, and so that the Z2, the integral of the F tilde Z dz is easy to evaluate. So how to find the F tilde? And this is not easy to find the approximate for Fz. So we can consider the 1 Fz and take the Taylor expansion of 1z as point z sub 0.
What's the Q? What's the QZ?
I use the QZ to represent the approximate distribution for PZ.
Oh, just one.
Yes. So ln Fz is is equal to 1. We only consider the first 3 terms of China expansions, and here we choose the point there is a zero according to here we have to choose the point is a zero. We take the first order derivative of ln fj and set it to 0. And with all this equation, we can get the point sub 0. And then we're using the capital A to denote the negative second order derivative of 1 fj as the point z equal to 0. And by choosing the point from this equation, we can make sure that the capital A is a positive integer. And later we check out why the capital A is should be a positive integer. And we take the exponential positive number. And then we take the exponential on both sides of this equation. Then we get the fj equal to fj times and we substitute this fj into the true distribution. Make us the pj equal to j. And we know that this part is not unnormalized. It's a unnormalized Gaussian distribution, and this is normalization constant. And the capital Z is on 1, but we can write this constant directly like this. And we write this normalized Gaussian distribution. So this is a normalized Gaussian distribution, and it is also the approximate Gaussian distribution. It's approximate distribution for P of Z. So we can say that the approximate distribution and the true distribution have the same mode, Z0. And here the capital A is a precision of the approximate Gaussian distribution. So the precision should be a positive number. So this is why we choose this point 0 to make sure that the A is a positive number, because to make sure the first order derivative of 1 and z equal to 0, the point the 0 is a local maximum. So yeah, it satisfies the capital A is a positive number. Then we will extend the Laplace approximation to the vector case. Now we suppose the height is an m-dimensional vector. With an m-dimensional vector. So to perform the Laplace approximation, we need to first calculate the first derivative of the ln fj and set it to be 0. Then we can get the point less than 0. and where the day I is equal to the first derivative of y f z respect to z of I. Then we calculate the negative of second derivative of y f z at point z equal to 0, and yeah, maybe I should change another. Yeah, it's called B. It's a.
So the rotation CI here, what CI mean?
ZI. Because here is a vector to take the
It's a
gradient
component?
vector.
Component of C? Why is that equal to CI? Isn't that supposed to be equal to zero?
Sorry. Sorry. I made a mistake. Equal to 0, then we can get the I.
Okay.
Yes, mistake. Then here we use a B that should differentiate that A. We use B to represent the precision matrix. And then we, after got this to component, we can get the approximate Gaussian distribution and Q of Z and C code.
For the second line, what's spelled out?
Then here is Z G1 F Z is equal to the VIG.
I don't think there's the common notation. I mean, yeah, it's okay. Just go ahead.
So then we can write the Gaussian distribution. B determined for B and 5.
But the second one, that is equal to B. Why you mean that?
Yeah, because in the scalar case, I use the A to represent the covariance,
No, I mean-
the precision. Yeah.
Why did you do that?
Why will do
For the
that
second,
for this line?
yeah.
Here's a matrix if you take the second order derivative with respect to Z. So B is a matrix. So we use the capital B denote a matrix.
Okay, you want B for what?
B equal to the second derivative of all
Yeah, B is
F
equal
Z.
to this.
Yeah,
and
okay.
evaluate
I mean, why did you just, why we want B?
because according to that previous case, B
Previous
is
in
the
the scalar case,
precision.
we got A
okay.
is the precision of the Gaussian
Okay, just,
distribution.
okay.
So here I want to difference the A and A. Yeah. So I use B
Yeah,
to
for the
represent
second-
precision
the second
matrix.
one.
Yeah. So here they had transpose B and they had A.
Or two.
Yeah, so this is approximate Gaussian distribution. So by performing the Laplace approximation, we want to do the prediction. Suppose we consider a boundary classification problem. Suppose for a boundary classification problem, we have the training data t and the new input vector x star, and we want to find the probability the input vector belongs to the class C1. So first we write this probability at the integral of the as a marginalization respect to the parameter omega. So C1 star t hat and d, and we write this. We also can write this probability as the likelihood times Weyl distribution, PC1 given x star p. So we know that this part we have been approximated by the Q omega using the Laplace approximation. So it is a Gaussian distribution with a mean 0 and A, B. B is a precision matrix. And for the boundary classification problem, this if we use using the logist regression, this probability is modeled by the logist function, right? H. Logist regression. It's a logist function. So in this case, it's called based in the logist regression. But the problem is the integral of logist function times the Gaussian distribution still does not have the closed form solution. So since we already using the Laplace approximation to get approximate distribution of prior distribution with respect to the omega, we want to find a closed form solution for the prediction. So if we consider other nonlinear function to model this probability, maybe we can find a closed form solution. Before we consider other nonlinear function, we will quickly review the properties of the logist function. For the logist function, the shape of the logist function is so the value is bound between 0 and 1, and for the omega times I is equal to the 0, and the logist function h of A is equal to the omega transpose times I is equal to the 0.5. So x we also know that this function is symmetric, so the h x is equal to the 1 minus h, and we also know that this function is a monotonic function. So we want to find another nonlinear function also satisfy these properties. And we know that the probability function the probability function is a cumulative density function of the normal Gaussian normal distribution. So it's a t to the t times x star. It's a Gaussian distribution. Maybe I use something PC or DC. And here PC is a normal distribution. C zero mean and variance is equal to 1. And the probability function also has the shape like this. So the integral of this function, this probability also bounded in the 0 and 1, and it also a symmetric function. It also a monotonic function. So we can consider to using the probability function to model the likelihood, this probability. And we also know that the integral of the probability function and the Gaussian distribution has a closed form solution. So we can use the probability function to model this probability. And in this case, it will be called Bayesian probability regression. So when you prefer to use discriminator model, and you want to have a closed form solution for prediction, and you may consider to use the probability function instead of the probability